There's a whole section devoted to the ligands. Remember, the ligands are the Lewis bases, and being ligands, they normally have a lone pair of electrons, like nitrogen does, or they have a negative charge for an anion. So ligands bind to that central metal atom. That could either be the metal itself or the metal in the ion form, and they make a coordination complex. So we talked about how some of them are octahedral, tetrahedral, square planar. You do not need to know what forms what. You only need to know that they are the options that are possible. So if I'm going to talk about a donor atom, it is going to bind to that central metal ion. There's two different types. One is called a unidentate, and that has only one donor atom. Or I could have a polydentate, and that is more than one donor atom. Listed below here are the oxalate, the ethylene diamine, and the EDTA. We also use them when we do naming. So they serve many functions. We're here to introduce them. Before I move on, here is the ammonia, which is a unidentate, and the chlorine. So this is the massive chart. I was going to break it down, but I said I'm just going to leave it in one piece. If you look here, it says monodentate, and each of those examples binds to the central metal atom via one donor atom. So ammonia, we've talked about that one a lot. The chloride ion, but you can see there's a whole host of different entities that can act as ligands. There's also the bidentate, and that means it's going to bond or bite with two atoms, and essentially ethylene diamine, we've got those two nitrogen atoms. Bipyridine, there are the two nitrogen atoms. Orthophenanthroline, two nitrogen atoms. Oxalate ion, it has at the minimum two atoms, and the carbonate can also bind to a metal center. The only thing I'd say here is you have to know that it is a bidentate ligand. When we get to the polydentate, that is going to be greater than two places where it bites. And if I just look at diethylene triamine, you can see there are three nitrogen groups that can bond to a metal. When we have the triphosphate, we can have more than one bond. And the one they seem to talk about the most is the EDTA. Now that has 1, 2, 3, 4, 5, 6 different places where it can bind to the central metal atom. And it is often used if people have been poisoned by toxic metals, because the F's for this are very, very large. The metal ion will react with that polydentate EDTA, and they use the word sequestered. And if it's sequestered, it is removed, let's say, from the bloodstream. But the whole idea of this section is to show you all the different kinds of ligands that there are. My last slide here, here is how they are represented, okay? If I look at this slide, I see these blue balls. Each of these blue balls represents a nitrogen that is bonded to a central cobalt atom. Notice also, I'm not good enough with the colors yet, but notice also there is a section here where we see a CH2, a bond, and then another CH2. Rather than draw that all the time, I'm just going to call it a ribbon. I know it's not a ribbon, but it looks like a ribbon. See this little piece right here? That would be the ribbon. That is really the CH2 group. So that's a shorthand that people use when they draw these complexes. So that is a cobalt amine complex, but down here is the EDTA. Now in the last slide, we said it can bind in 6 different places, and it is represented by the figure to the right. The reds are oxygens, the blues are nitrogens, and you can see how it really sequesters, surrounds that metal ion. Notice, just for an example, if I have a copper ion in the center, the K is on the order of 10 to the 18th. It is essentially totally gone to form the products. That's why we had all those other chapters. So when you move on to your other courses, you can understand better when they give you some information. The next slide talks about the chelate effect and entropy. Okay, these are all things that you already know. We just want to put them into practice. If I have a polydentate ligand, it will have a more stable compound than a monodentate ligand. So let's just look at the values here. I see a K of a 10 to the 9th. I see a K of 10 to the 17th. The 10 to the 9th is when I have the monodentate ligand. The 10 to the 17th is when I have that EDTA ligand. So you can see if I can bind in more than one spot, I will form a more stable complex, okay? The second example, I just put it in there because, again, it is showing you why we did everything we did before we got to this chapter. The delta H zeros for these two copper compounds, this time it's a copper. Up above was a nickel. The copper compounds have a comparable delta H's, but look at the difference in the delta S's. The ethylene diamine has a positive 23. The amine has only a negative 8. Humongous difference. The delta G0, look at how much more negative it is with the ethylene diamine, meaning you are going towards a spontaneous reaction as written, versus the amine. Now, I'll be honest, there are lots and lots and lots of different compounds. You don't need to know what they are, you just need to know about the chelate effect. How if I have a nitrogen-based ligand, it can form a complex. And we would start with, again, just a plain old copper ion. And what would happen is we would actually have these things form. And as you can see by the Ks, 10 to the 7th with a copper, 10 to the 10th with an ethylene diamine. So it's the amine, it gives you a 10 to the 7th. It's the ethylene diamine, gives you a 10 to the 10th. So this is really a short video, but it's really to talk to you about only the ligand. They can be monodentate, they can be bidentate, they can be polydentate. And we have known that when we go into the lab and we make some compounds, if we use something that is a polydentate, it will be more stable than a bidentate. That will be more stable than an amine.